Hello and welcome to video 2 of 2 dealing with the components of force vectors. This video, number 2, is designed to discuss the mathematics and the application of math to the components of force vectors. It is a companion to the first video, and it is recommended or suggested that you watch part 1 first to give this video some meaning or context. I'll begin this video with the understanding that you've already watched the first video, or at the very least, understand the basics of vector geometry from a previous math class, or perhaps from an introductory course on physics. In order to understand how to quantify or apply mathematics to vectors and their components, you must have some recollection of basic right-angled triangle geometry from a previous math class, perhaps in grade 10 academic math. The basic right-angled triangle is comprised of some very basic parts. We give names to the three sides. We have a right angle here, and we have two other angles. The sum of the three angles interior of the triangle adds to 180 degrees, and there are many relationships. Pythagorean theorem can be applied, as well so can trigonometry. So let's go ahead and define the names of the sides of the triangle and what they mean, because we're going to be making use of them. First of all, we have an angle, interior angle, that I'm going to call theta. I could easily have chosen this one. I have to choose this one because of the orientation of the triangle. This, of course, is a right angle, and now we can name the sides. As you recall, the name of the side of the length of the triangle across from the right angle is called the hypotenuse. The name of the side of the triangle across from the defined angle theta is referred to as the opposite, because it is, of course, opposite this angle. And in reference to this angle, this side is referred to as the adjacent, and again, because the word adjacent means beside, and this length is thought to be beside this angle. It's hoped that this triangle reminds you a little bit of something you saw in the first video. I had also drawn a triangle in that video, and this video should remind you, or this triangle in this video should remind you of that triangle. Do you see a resemblance? What do they have in common? How are they different? There exists in mathematics in the right angle triangle some very basic but very powerful relationships amongst the lengths of the sides of the triangle and the angle contained within. These relationships with this angle and the three sides are trigonometric relationships, and they involve the ratios sine, cosine, and tangent. So you'll recall that the sine of the angle contained within is equal to the ratio of the magnitude or the length of the opposite side divided by the magnitude or length of the hypotenuse side. Similarly, the cosine of the interior angle defined, theta, is equal to the length of the adjacent side divided by the magnitude or length of, once again, the hypotenuse. There is another ratio, one that we're not going to use specifically for looking at components, and it is a tan ratio. The tan of the angle theta is equal to the length of the opposite divided by the length of the adjacent. And you may remember the saying SOHCAHTOA as a way of remembering these relationships. Sometimes we want to rewrite this relationship so that we are trying to solve for one of the sides of the triangle if we happen to know the angle. So we can play around with this equation by cross-multiplying, or more appropriately what we're really doing, if I'm solving for the length of the opposite side, I will multiply both sides through by the hypotenuse. And of course, when I do to one side, I must do to the other. So I can now say that if I don't know the length of the opposite side, but I do know the length of the hypotenuse, and I do know the angle contained within, then I can multiply those two together and get the length of the opposite side of the triangle. In a similar way, the adjacent, the magnitude of the adjacent side can be determined by multiplying the magnitude of the hypotenuse by the cosine of the angle contained within. These two forms of this equation are very important because they allow us to identify or to calculate the length or the magnitude of the two sides of the triangle. Now let us turn away from mathematics specifically and apply this mathematics to our force triangle that we looked at in video number 1. What I'd like you to do right now is to pause the video so that you don't go on and look ahead just yet. And I'd like you to redraw this triangle by using a force vector and the components of that force vector. And then you can see what it looks like and how well you did. Okay, how did you do? If you replaced the hypotenuse with the applied force vector, that's absolutely wonderful. That's exactly right. Now you'll notice I'm missing two sides of the triangle here. I will fill them in, and you can compare how you did. So here, for example, might be one of the sides of the triangle, and here, for example, might be the other side of the triangle. So if you ended up with something like this, congratulations, that's very well done. You're well on your way to understanding component math. If we think back to video number 1 where we had our little green object that was being pushed, now maybe you can see some context for this. We're going to push this with some magnitude of force in the x direction, and at the same time, and I can just slide this vector over, of course, because I can translate vectors, I'm going to give it a push in the vertical or y direction, or north if you want to think of it this way. I'm going to do that simultaneously, and that will be the behavior or the trajectory or the path, if you will, that the box will take. So now what we want to do is we want to define these components of this applied force vector. And we're going to use our trig to do that. Once again, this is my defined angle. That is to say the little green box moved some angle to the north of east or above the x-axis. You'll recall the new term that I introduced last video. The process of breaking down a two-dimensional vector into its two one-dimensional components is referred to as resolving a vector into its two components. The two components are always at right angles to one another, and they are scalar quantities, not vectors. What we want to do now is we want to identify or name these components like we've named this vector, the applied force vector. There is no universally accepted convention for naming components. Many authors, many professors and teachers have their own unique way that they identify these two components based upon what they might have learned when they were in school. What I tend to do is I tend to identify these components mostly using x and y. However, north and east and south and west could come into play as well. So I'm going to refer to this component as the applied force. And we want to make sure that when you subscript, that the subscript itself is not as big as the symbol for the quantity. And that is in the y direction. You may alternatively see, and this I use as well sometimes, f sub y for simplicity. This, of course, then, if we apply that rule, would be the applied force, or the component of the applied force in the x direction. Not only will you see different ways of identifying the name of the component, you will also see some differences in terms of how they are drawn. In some cases, you might see components that are drawn with dotted lines. For example, you might see something like this. Or alternatively, you might see a component that does not have an arrowhead on it at all. Again, different people use different methods of showing the components of the vector. So of course now, what you've all been waiting for, the math. So we'll try a worked example here, a very simple example, but what we're going to do is we're going to ultimately determine the magnitudes of the two components of this particular vector f applied. So what I'm going to need is I'm going to need some data, some values. So we're going to call, for sake of argument, f applied will be 5.0 newtons. Notice the precision. I have two significant figures here. That's important in our end answer, 5.0 newtons. And I'm going to define this angle theta in here as being, let's say, 37 degrees. Actually, to better suit this particular problem, I'm going to define theta as being 53 degrees. Don't forget the degrees symbol. It is a unit. It does need to have a symbol for the unit. So now we're going to set it out, and we're going to try to identify what its components are. If you'll recall from previous screens that we looked at, the length of the hypotenuse, or the opposite, and the length of the adjacent are similar. The length of the opposite side, which we now know is going to be our vertical or y component, is simply the magnitude of the applied force times the sine of the interior angle, and similarly, the length of the adjacent component will be the magnitude of the applied force. Remember, again, it's a scalar, it's a magnitude, times the cos of the 53-degree angle. So if we write out that equation, I'm going to start by doing the adjacent component first. So I'm going to write out that the, we'll call it, actually, we'll just call it fx for simplicity here. That is the magnitude of the force in the x direction is going to be equal to the magnitude of the applied force. Again, we do not put vector notation on top of these because these are not vector quantities, it's just the size of the force. Times, since it's the x component, it's going to be the cosine of 53 degrees. Solving that, we can simply say that that is going to be 5 newtons of force times the value of the cos of 53 degrees. Now, to find out the value of the cos of 53 degrees, it's really quite straightforward. We are just going to simply change this to a color you can see for a moment. So what you're going to do is you're going to simply type in, first of all, make sure that your calculator reads degrees up here and not radians or radians. And you'll simply type in 5.3 in your calculator, and you'll hit the cosine button. And when you do that, you should end up with 0.601815 with a number of other digits afterwards. Use all the digits in your calculator, never round early. Always keep all of the digits that you see on your calculator until your final calculation. So I will simply now replace cos of 53 and do my calculation, and therefore the magnitude of the force in the x direction, if I'm going to multiply that now by 5, I end up with 3.0091 as the force magnitude in the x direction. To the proper number of significant digits, which in this case is 2, you should try to predict what I'm going to write here. The magnitude of the force in the x direction is 3 newtons. The newton, of course, being the unit for the magnitude of force. Notice again, formatting, my equal signs should all be lined up vertically, one above the other. I always finish off with my unknown and a unit, and nothing is written here on the right-hand side. To now do the component in the y direction, I do the same sort of thing. I take f sub y, and that, of course, is going to be equal to the magnitude of the applied force times the sine of 53 degrees. I substitute in my known values, proportion to 2 significant digits. The applied force is 5 newtons. And now I need the sine of 53 degrees. And when I calculate the sine of 53 degrees, I get 0.7986 with some more digits following. And when I multiply those two together, I get force magnitude in the y direction of 3.99, oops, not y, 3.9932 newtons. Once again, when I use my proper rounding rules and significant digits, the fewest number of significant digits is 2, so this will round to 4.0 newtons. So what does this mean? What exactly do these two magnitudes mean? And ultimately, how do they relate to this magnitude? Well, hopefully you gave some thought to the meaning of this particular component in the x direction, 3 newtons and 4 newtons. So once again, if we go back to our little green block, if I apply a force of 3 newtons to the right or to the east or in the positive y direction, horizontally if you want to think of it that way, and I apply a force simultaneous to that of 4 newtons at right angles to this force, then the resultant force will be 5 newtons at a 53-degree angle to my reference line, my x or easterly direction. So I might write out then as the final vector for my applied force. I might say the applied force. And in this case, it really is a vector because I'm going to attach a direction now. Is 5 newtons to the east, 5.0 newtons, and now I'm going to say east. And again, there's different notations for this. You may have learned one slightly different. East, 53 degrees to the north. You might also have heard it as being 53 degrees north to the north of east. That's also perfectly acceptable, of course. So we successfully resolved this vector into its two components. One component has a magnitude of 3 newtons to the right or to the east, and the other component is 4 newtons to the north or up, or the y direction. Now, as you might imagine, or maybe you are already thinking ahead, that if either of the two magnitudes of force should change, should this particular force vector become larger while the y direction stays the same, well then I would have to slide this vector over and then I would have to complete my triangle, and that's now going to alter the angle. It's not as steep, meaning that the applied force vector is becoming closer to the easterly component. And if I made this vector even larger at the expense of this one staying the same, then it's becoming even more towards the east. And you can imagine that if this vector became even larger and larger, then ultimately the applied force vector would become closer and closer to being completely due east or only one component. Now, please take note, I'm only choosing here the northeast quadrant, or the first quadrant of the Cartesian plane. All of this would apply over here in the northwest, down here in the southeast in quadrant number 4, and over here in quadrant number 3 on the Cartesian plane in the southwest. The exact same math will occur. I just arbitrarily chose to work up here in the top right quadrant. Similarly, this analysis that we went through involving determining the components of this force vector, this would apply equally to a velocity vector, a position vector, or any other vector. Any vector can be broken down to or resolved into its two perpendicular components. So now that you have some understanding about the components of the vector and how the components, the magnitude or the lengths of the sides of the triangle, the components, affect the resultant or the hypotenuse, you can see now that as I move this around, let's say we choose a force vector like this. In this case, you can see that there is very little contribution in the x direction and almost all of this force vector has a component in the y direction. Similarly, down here, almost all of the force is directed to the east with very little bit of component directed to the north. And we have everything in between. Ultimately, if I have a vector that lies collinear to or along the x-axis, there is no y component. All of the component is strictly in the east or x direction. Okay, I'm going to do one last example. This is more or less a real-life example. It'll be an example of a skier or a snowboarder or a tobogganer or some such thing as that on very slippery snow, very cold, dry snow, very icy, so the friction can be negated. That the coefficient of friction is very, very low. It's essentially zero. So I'm going to start off by drawing a system diagram, and that system diagram will look something like this. Here's my reference level, horizontal, and I'm going to have some hill inclined at some angle. The angle doesn't matter for these purposes. It's just some angle. I'll give it a fairly steep slope, like so. And so this angle I'm going to define it here as being theta, as we typically do in science and physics and math. And I'm going to identify some generic object. This could be a skier or a snowboarder standing stationary on a hill, and we want to analyze the forces that are acting on this object at the point of not moving, so it's momentarily stationary. So you may recall from previous classes in physics that there is going to be a force of gravity that is acting straight down, as gravity always does. And I will identify that force as being mg, which of course, if you've studied this, you know that the force due to gravity acting on a mass m is simply the product of the mass m times the gravitational field strength g for that particular moon or planet. The other force we know for sure is the force that is referred to as the normal force, and this is a support force. This is the force that acts at right angles to any slope. So this force vector is always at right angles to the surface that the object finds itself on. These are the two forces that are acting on the object. What we want to do is we want to resolve the force of gravity vector, mg, into its two scalar components. So in doing so, we need to, once again, form our triangle. And so one side of our triangle will look something like this, and the other side of the triangle will look something along the lines of this. Now they don't completely fit, so I'm going to just increase my mg slightly so that the triangle fits nicely. Now, this triangle should look familiar. It's a right angle triangle, and we have some angle, theta. The angle theta, the inclination, or the angle of repose, as it's sometimes referred to, is also this interior angle here. This can be demonstrated by using similar triangle math or congruent triangle math. Angle, angle, angle similarity will tell you that these two angles are the same. And I think intuitively, you probably would understand that if I close this angle down so that the hill becomes less and less and less steep, that these two vectors will end up being collinear, and this angle will also collapse. And actually the situation would look something similar to this, where there's the force of gravity vector, there's its component right here, and the normal force vector pointing up. All right. Due to the geometry of the situation, you will find that the length or the magnitude of this component, again, remember the components are at right angles to each other, and the components are the non-hypotenuse side of your vector triangle. So here is the hypotenuse. The triangle is just slightly rotated this way. If you rotated it back through this angle in here, then it would look like a normal triangle that you're familiar with. These two are the components. This component, which is the component that is perpendicular to the surface and is opposite the angle theta, is the magnitude of the normal force. This force is the normal force, This magnitude, or the magnitude of this component, is also the magnitude of the normal force. This vector, which actually originates, we'll get it here, right here. This is a vector that is trying to drive you or the snowboarder down the hill. It really is the applied force that's acting on you or on some object. And its orientation, as you saw, is parallel to the ski hill. This vector is parallel. As such, the notation or nomenclature, we sometimes call this the parallel component because it is parallel to the ski hill. Remember, vectors can be moved anywhere you like, just don't change their magnitude or direction. This vector is often referred to as the perpendicular component because it meets the ramp or the slope surface at right angles. So once again, before I proceed, pause the video and see if you can correctly identify what these components are. So for example, the normal force, what part of the force of gravity vector mg, what part does this represent? Similarly, this force vector here, or this component that ultimately is driving the object down, the applied force on the object down the ramp, what part of gravity is this? Well, what did you come up with? Let's look at this component. Since it is opposite the angle, it is going to be the sine component. The hypotenuse of this triangle is simply the magnitude of the force of gravity, mg. So remember from before, go back and look at the video from before, it's always the hypotenuse times the sine of the angle, or by the cos of the angle, sorry. So this is mg cos theta. Sorry folks, I thought ahead a little bit and I made a mistake here. This is the angle in question. I apologize for any inconveniences caused you. It's this angle, this interior angle is theta. I was thinking back to the previous triangles that I had done with you and always talked about this angle. This is the angle theta. So once again, if I was to close down this slope by making it shallower and shallower, these two vectors would become one, or these two line segments would become one. So this is the angle. So this is the opposite. This is the adjacent. Hence it is cos. I apologize for that. Similarly, then, this component is mg sine of the angle. And there you have it. These are the two components. So this is sometimes referred to as F parallel or F applied. So sometimes you'll see this notation, F applied equals, or you might see sometimes this notation, F parallel, meaning the parallel component. This ultimately is the magnitude of the force that causes the object to slide down the hill. Of course, there would be a force of friction acting backwards in this direction. However, we've said that friction is essentially approximately zero, so it doesn't come into play. An interesting thing now is to look at this angle. Let's start to put some angles in and see how things change. Sometimes I like to look at extremes. What if the angle was 0 degrees? Well, if the angle was 0 degrees, we would have a horizontal surface with a skier standing on a horizontal surface. I think intuitively you would understand that gravity would not contribute to driving the skier forward as long as the skier was on a horizontal flat surface. As such, if I replace theta with 0, the sine of 0 is 0. The force due to gravity, mg times 0 is 0. And so we can say that there would be no parallel component. In other words, the component in this direction would be 0 newtons. On the other hand, if the 0 degrees is replaced in here, the cos of 0 is 1, and 1 times mg is 1. So we have a force of gravity acting straight down on the skier, and of course we've got a support force that's holding the skier from falling through the snow, and that is F sub n. And in the case of 0 degrees, these two are equal but opposite forces. They have exactly the same magnitude, always, but they are directed in different directions. Now, what if we replace 90 degrees or theta. We go through the same math. The cos of 90 in this case is 0, and that means that this normal force becomes 0. Well, under what circumstances would the normal force become 0? Well, that's when the ramp angle is 90 degrees. So in other words, this. And if I have some object that I place on my slope, there is no force at right angles to the object to support it. So the object simply undergoes free fall in a frictionless environment. There is no normal force. If I take my 90 degrees and I replace theta with 90 degrees, I find that the sine of 90 is 1, and therefore the applied force of the parallel component is in fact simply mg directed straight down. It is the force of gravity. And so the only component in this case would be the force of gravity component, and there would be no component acting this direction supporting the object. As I take my slope and I start to make it shallower and shallower, I begin to bring about some normal force. I introduce some normal force. And the force of gravity driving it down the slope becomes less and less and less and less and less until eventually, to this extreme, all of the force is normal force and there is no force of gravity driving the object down the ramp. So in this case, although there is a force of gravity this direction, of course, there is no component of the force of gravity horizontally. So unless there is some other force, a force of the skier's muscles on the pole of the skis, or a very strong wind, there will be nothing to move the skier, in this direction. So to summarize, for our last example involving an object on an inclined plane, where we have this object like so, there is a force of gravity vector mg that acts straight vertically down, and there is also a normal force vector that is perpendicular to the surface, and there is some angle theta. The two components that we're concerned with are, one, the component of the force of gravity, which is simply the magnitude, the length, the magnitude of the normal force, and this parallel component to the force of gravity, mg, that is actually responsible for accelerating the object down the ramp. And if I write expressions for these two components, the perpendicular component, the normal force component, is going to be equal to mg cos theta and the parallel component, or the component that goes along the slope, the applied force as it's often called, I'll just call it the applied force here because ultimately it is the force that is applied to the object. Its magnitude, again remember these are magnitudes, is equal to mg sine theta. It is this and this that give us the component or the part of gravity, because this will become a decimal and this will be a decimal, and that will be some part or some fraction of m times g. Thank you very much for watching the video. I do apologize for that one slip up on the angle. It happens to the best of us, and hopefully it didn't cause you much concern, and that you've learned something about the mathematics of